The solar neutrino problem refers to a discrepancy between the predicted and the observed number of neutrinos produced by the Sun. The problem was first identified in late 1960s and early 1970s and was a major puzzle in the field of solar physics for several decades. Neutrinos are subatomic particles that are produced in huge numbers by the nuclear fusion reactions in the Sun's core. These neutrinos travel through space at a nearly speed of light and can be detected on Earth using specialized detectors. The number and the energy spectrum of these neutrinos can provide important insight into the process that occurs within the Sun. In 1960s, a number of experiments were conducted to measure the number of neutrinos produced by the Sun. These experiments used detectors located deep underground to shield them from other sources of radiation. The results from these experiments were surprising. The number of neutrinos detected was only 1/3 of the number of predicted neutrinos from theoretical models of the Sun's interior. This discrepancy, known as the solar neutrino problem, was a major puzzle in the field of solar physics. It seemed to suggest that our understanding of the process that drives the Sun's energy production was incomplete and incorrect. Over the years, a number of explanations were proposed to explain this discrepancy, including possibility that neutrinos were changing flavor that they travel from the Sun to Earth, or there are errors in the experimental methods used to detect them. One possible explanation for this discrepancy was that the neutrinos were changing form or flavor as they travel from Sun to Earth. Neutrinos come in three different flavors: electron neutrinos, muon neutrino, and tau neutrino. The detection experiments were designed to detect only the electron neutrinos, but if the neutrinos can change flavors, then they could transform into muon or tau neutrinos, which are not being detected. This idea is known as the neutrino oscillation and was first proposed by Bruno Pontecorvo in 1950s. The theory of neutrino oscillation was later refined by theorists like Bruno Pontecorvo, Jiro Maki, Masami Nakawa, and Sakata Toshio, who introduced the concept of mixing angles between different neutrinos. To test the theory of neutrino oscillation, a series of experiments were conducted using large detectors placed deep underground to shield it from the cosmic rays. The first of these experiments was the Super Komiokande experiment in Japan, which observed the neutrinos from Sun and found that the total number of detected neutrinos matched the predictions of the solar models, as well as the total number of electron neutrinos matched the number which were detected earlier by different experiments. This provided strong evidence for the theory of neutrino oscillation and solved the long-standing solar neutrino problem. The resolution of the solar neutrino problem was a major breakthrough not only in the field of solar physics, it even changed the theoretical physics. According to standard model of particle physics, neutrino oscillations are not possible. Therefore, it is still a big puzzle for particle physicists. It demonstrated that our understanding of Sun's interior process was largely correct and provided an important insight into the nature of neutrinos and their interactions with matter. It also highlighted the importance of experimental verification of scientific processes and the need to continuously refining our understanding of the universe through careful observation and measurements. In conclusion, the solar neutrino problem was a major puzzle in the field of solar physics for several decades. The discrepancy between the predicted and observed number of neutrinos led to a number of proposed explanations, but it was ultimately resolved through a careful experimental verification. The resolution of this problem provided important insights into the nature of neutrinos and their interactions with matter, and demonstrated the importance of careful observation and measurement in the scientific processes. So thank you for watching this video. We hope that you found this information informative and helpful. If you have any questions or comments, please feel free to leave them down below. Don't forget to like and subscribe to our channel for more videos like this. And also don't hesitate to share this video with your friends and family who might find it interesting. Thanks for tuning in, and we'll see you in the next video.